Hello and welcome back. In today's video, we are going to study one-dimensional heat conduction through a pipe. So, what we are going to do is we have a pipe which has some inner radius and some outer radius. So, it will be its inner diameter, and this will be the pipe's outer diameter. So, what we have to do is we will see or we will study the heat transfer along the radial direction of this pipe thickness. If we see this circular cross section of the pipe, so it will be something like this. It will have inner radius and it will have outer radius. So from the theory, we know that flux, we know that the flux will be 2 pi k L T inner minus T outer divided by ln outer radius by inner radius. This is the heat transfer that we find, heat transfer through this thickness along this radial direction. And if we want to find the temperature at any point along this radius at any thickness, so temperature at any radial point R is initial temperature minus this heat transfer rate that we find divided by uh, 2 pi k times ln r by r inner radius. So these are the two basic equations that we are going to use in this case, study one-dimensional heat conduction. So heat transfer rate and the temperature distribution equations. So let's move forward. So we have a problem, and we will obviously this is a study problem that we are going to study, so there will be no involvement of time. So the uh, problem says inner pipe radius is 0.02 meters, and the inner side the temperature is 200 degrees Celsius, and outer radius is 0.05 meter. Temperature on the outer side is 50 degrees Celsius. Thermal conductivity of the material is 15 watt per meter Kelvin. And because this is all that we are going to need for our problem, we have to calculate the heat transfer per unit length and temperature at this radial point. So first we will solve it analytically, and then we will use COMSOL to solve the same problem to compare the solutions. So let's move on. So we know that the heat transfer rate will be 2 pi kl T inner minus T outer divided by ln of R outer by R inner. So we have to find heat flow rate per unit length. So we have to take L1 for 1 meter length of the pipe we have to take. So let us first of all calculate this term, R outer by R inner. So this will be ln of R outer is 0.05, inner is 0.02. So this will be, if we calculate, this will be ln of 0.05 divided by 0.02. It is 0.916. 0.916. So it will be 0.916 this term. So let's now so heat transfer rate will be 2 pi k. K is 15 in SI units, L is 1, and T inner surface has 200 degrees Celsius, outer has 50 degrees Celsius. So when there is difference, so whether we take temperature in degrees Celsius or Kelvin doesn't matter, they are going to cancel out 273.15 divided by our value 0.91616. So when we calculate this value, it will be 2 times 3.14 times 15 times 150 divided by 0.916. So it is approximately 1542.76 or 8 watt per meter length of the pipe. So this is our heat transfer rate. Now moving on, we have to calculate the temperature at a radius of 0.03 meter. So it is T initial minus this heat transfer rate that we have found divided by 2 pi k ln of R by R inner. So let us write, first of all, let us write R here. So we have this is the temperature distribution along the radial direction. So temperature at a radius of 0.03 meter will be initial inside temperature is 200 degrees Celsius minus Q dot that we found is 1542.5.8 divided by 2 pi k is 15 ln of R that we have to find temperature at is 0.003 divided by inner radius is 0.02. Let's solve this first. So let us start with ln of 0.03 divided by 0.02. So this is 0. This term we have here is 0.405. Let us solve all the terms now. So 200 minus bracket 1542.5.8 divided by 2 divided by 3.14 divided by 15, and we will multiply this by 0.405405. So our temperature at 0.03 meters is 133.67, which is 0.7 degree Celsius. This is the temperature at that thickness. So we will now solve the same problem using COMSOL Multiphysics software, and we'll compare the solutions. So let's move on to COMSOL Multiphysics. So open model wizard, we will choose 3D heat transfer in obviously solid. Then our study will be stationary because we're not calculating anything with the time. So here we are inside the COMSOL. First of all, let's make geometry. Our geometry will be right click on the geometry cylinder. So let us make inside cylinder. It is radius is 0.02 meters and length, which is height here, is 1 meter because we are calculating per unit length. So we'll build this. So this is our pipe, inner pipe. Now we will duplicate this cylinder, but we will make it 0.05 outer radius. Now this is our pipe, but we have to make it hollow inside. So for that, we right click on the geometry, we go to boolean and partitions, then we choose difference. We have to make difference. Now objects to add, the object that we have to keep is means this object to add. Excuse me. Then object to subtract, the object that we have to subtract from here is the inner cylinder. Then we will build all, so we have hollow cylinder inside that we can see. Now geometry, we're done with the geometry. Let us go to heat transfer in solids. Then we'll go to solid section and we'll choose thermal conductivity user defined, and the value will be 15. We don't need other properties. If we want to insert other properties. We can insert any values, because for stationary study, though these properties won't matter, all that we need is this thermal conductivity here. So initial value, let's keep it default. Now we have to apply the Dirichlet boundary condition. There's a constant boundary condition here, temperature. So temperature on inner walls. So we have applied on the inner walls, inner surface. So temperature we have to uh, keep here is 200 degree Celsius. Let's insert temperature again here. Now we will choose outer boundaries. Now we have 4 boundaries on the outer and 4 boundaries on inner. Okay, now the value on the outer boundary is 50 degrees Celsius. So 50 degree Celsius temperature on the outer surface. So we have applied boundary condition. We'll mesh it. So the meshing is done. I kept a normal element size. Then we'll go to stationary and we'll compute. Now after computing, we have our results here. Now we have to calculate heat flux. So for that, we'll go to derived values. We'll calculate, we will integrate our surface integration, because we have to calculate heat flux at the inner surface. So here the expression chooses temperature. We have to choose boundary heat flux. We'll calculate, we'll select a normal, because we have to calculate heat flux normal to the surface. So normal total heat flux, we'll choose this, and for that we'll choose these inner surfaces, because we want to calculate the flux total heat transfer through the inner surface, because inner surface at higher temperature, outer surface lower temperature, so heat will be transferred in this direction radially outwards. So I'm choosing whole inner surface. So when we calculate, the value that we can see here is negative 15436. Negative means, so we know that when a vector is normal to the surface outside, it is positive. When it is inner side, it's negative. Heat is being transferred from inner surface outer surface, so vector on the inner surface will be inward, so it's negative. So our interest is with the magnitude of the heat transfer, which is 15436. We can see 15436. Our analytical value is 15426 approximately, and our COMSOL value is coming out to be 15436, which is close. These are round of errors and the discretization error. So this is almost the same. Now the second thing that we have to calculate is the temperature at 0.03. So for that we have to first of all insert a point at that location. Then we have to point evaluate temperature at that point. How do we insert points liners? We go to the data set, we right click, we select a cut point 3D, because we have to insert a point in 3-dimensional geometry or cylinder here. So it should be at some, this point is 0.02, this point is 0.05, so it will be in between. Let's make it at the halfway. So let us choose x 0.5, and let us choose y, our value 0.03 meter, at which we want to calculate this temperature, and z again 0.03. So we have to make sure the temperature at which that we are calculating is exactly at 0.03. Remaining 2 points we can choose accordingly. So when we plot, so okay, 0 not 0.0, let's make it 0.0, 0.5, sorry. So our coordinate, our point should be somewhere here. X, okay, we have to choose y is this direction, so thickness should be clearly 0.03, and x is another radial direction 0. Okay, x has to be 0. Okay, now it is perfect. Now it is perfect. Okay, now it is perfect. So we have to choose coordinates to locate our point wherever we want to find our value. Now let us go back to point evaluation, cut point 3D. Now we'll evaluate again. Okay, now we have our value. Let's delete this. Okay, now our value at 0, 0.03 and 0.5 is 133.46. 133.46 is almost 133.5, and our analytical value is 133.7, which is nearly the same. So the values calculated through COMSOL multiphysics and the analytical method are almost the same, and we know this little differences because of the discretization error and the round of errors. So this was all about today's video. Thank you.